Okay, we'll go ahead and get started. Let me go ahead and open us up in prayer, and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, thank you for the chance to be working with each of the lives of the students here in this course. I pray that the material that we cover will be clear and enjoyable. It's going to be helpful for them to get the jobs of their choice, as well as or the starting a business of their choice. I pray also that you would help them in their spiritual formation, Lord, that the time that they're getting a chance to study scripture is going to be helpful for them to navigate in the future to get a better sense of how these things can be used in our day-to-day life and be derived in the theological concepts that we want to be familiar with and using. And finally, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're finishing up the third major section that we have in our textbook today. And so we'll be going over digital logic and also want to have us think in terms of the work that we're doing in our project work as we've been doing so far. And so we've completed our first assignment, which was the digital logic, but this will be a reminder and then an extension of that to why this is something important for us to become familiar with in terms of computer architectures and organization. I'm going to do a poll. I'll do it at the end of the course too. How many people have their Arduino units? If you don't, I'd recommend that you get them right away because it's going to be important coming up fairly quickly. And when I do our lab time that I do more on Thursdays, I'm going to be starting to showcase some of the Arduino kits work. Go ahead.
Is there a link in the syllabus or anything to which one you want us to get?
Yeah, there is. Well, having problems with the display here, but let me quickly end this. It'll probably stop the screen share, but let me go ahead and just go to our course. So if you go to computer architectures and project related, no, that's not it. Sorry. Project resource information. And then under the Arduino unit, so this is an example, one that I had picked to give you an idea. Okay. So please go ahead and get your Arduino kit as soon as possible. Let me make sure I'm sharing my screen again, and I'll show that link again, and then I'll go back to what we're covering. So this is the one that I have here from Amazon. I think we're going through Amazon's big sale right now. So if you haven't already got it, you can save a little bit of money on the project. So fairly affordable. And this has a nice complement of things that we'll be leveraging, a few things that might be a little bit more advanced. And we're going to start to showcase some of these things mostly on Thursday. So just keep that in mind. So what we're going to get a chance now is just to be thinking in terms of digital logic, but let's think about it from the perspective of why it makes a difference. We'll get this moved over again. Sorry for those that are seeing this online. I'm trying to get this thing to move. Always nice when technology works. Sometimes you have to finagle it a little bit. Okay, so this is the things that we're going to be covering. And so we did digital logic in our first project, but now we wanted to be thinking about it in a larger context of why it's important for computer architectures and the kind of decisions that we would be leveraging. So first, we get a chance to be thinking about Boolean algebra. So we'll do a little bit of review. You guys have had a first encounter with the gates, and so we'll summarize that. And then we'll start to be thinking about the combinational circuits. And so this is where it's starting to now leverage that kind of capability and see how this is going to be helpful for us to do some of the things that computers do that we, for the most part, don't think about. And so first we talk about combinational circuits. We'll introduce topics like multiplexer. Anybody have ever heard the term multiplexer? I think some of the engineers in the room might be familiar with that term. So sometimes it's called a mux, and then there's also a demultiplier, multiplexer or a demux. We'll look at various ways that you can be doing using digital electronics for things that we do in a computer, like adding. Then we'll talk about sequential circuits. And so flip-flops is the basic building block of how we remember something in computers. You stick them together and you call them registers. There's an ability that you can do a counter. Some of you actually used a counter in your digital logic circuit, and so that might be helpful. And then there's these different kind of chips where inside what it has is a lot of these different gates, but you can program it to do certain kind of complex operations, and I'll try and give you a little sense of what that's all about. So let's just dig into this. And so Boolean algebra was named after George Boole. He proposed the basic principles in 1854, and it's really caught on. And Sean Shannon suggested Boolean algebra could be used to solve problems in relay switching circuits design. And that's what we're going to be leveraging here. I'm going to do it in more of a survey fashion. You can read Stalling to get more details, but you can get a better sense of what that's all about. And hopefully by the chance of going through this, it'll make it easier. And so here we can see from a Boolean algebra, bless you, these different things here, like an AND gate, A and B, an OR gate, A or B, or not is you invert it. So these are the three basic digital things that we've looked at. So we can have a description, and here in terms of an algebraic expression, how it would look, you can be using this symbol here to represent if it's this way, it's and, if it's the other way upside down, it's an or you put a line on the top that typically means that it is an inverted or not. So those are the basic elements that we have. So there's a various ways that we can be thinking of it. We can be thinking of them as true and false, 1 and 0. And another, if I'm thinking more of a hardware sense, it could be like the classical way of the voltage levels. It would either be 0 volts or 5 volts. I won't use that perspective very often in the context of this course, but that's another way that you could be thinking about it. So then we can start to be putting together these tables of Boolean operations, the not, the and, the or. Then we had these other ones we talked about, NAND, NOR, and exclusive OR. And so this just gives you an idea if you have two inputs and you put them in the input of a gate, what it actually implies. It may be a little bit easier to track this by looking at it from these Venn diagrams of what they are. And so A, if we're just that, and so not would be anything that's outside of A for this whole domain. A and B, so this would be an AND gate, so that's the what it would be. An OR gate is more inclusive. It's A and B, or when it's only A and only B, that would also be there. An exclusive OR means only when it's just A or only when it's just B. And NAND A is just the inversion of the and A NOR A is the inversion of the OR. So that just gives you an idea of what that means. And this is just a Venn diagram for 3 Boolean variables. I'm just going to skip over that for now. But you can see that in the center, just to give one example, this means that it is A, B, and C. So thus we have 3 here. So the first one would representing A, the second one would represent B, the third one would represent C. And so we can just see how this works by looking at the details of that Venn diagram. So there's various identities, and so you can be thinking of algebra, but now we're thinking of Boolean algebra. And here is the various ways that you can be thinking of those different types of gates. And the ones I prioritize the most for our project work is these first 3. And these are just more complicated variants of those that some of you have had a chance to utilize. So I mentioned before that NAND gates are actually easier to produce. And so if you were to get something like an FPGA or something where you're trying to have all these kind of these things here, these logic gates, the simplest one in terms of the least amount of resources would be a NAND gate. And there's also the OR gate that is similar. And so we can actually mimic these functions by putting together various NAND gates to get these other things. So you can get an AND gate, you can get an OR gate, or you can get an inverter by using a NAND. So that's what I'm trying to show there. And here's something simpler. We can do it with a NOR gate. We can just get an idea of how that would be utilized from that. So here's an example of a Boolean function of 3 variables. And so you have 3 inputs and you have an output. And so here could be like an example, like Nathan with his home security system, that there's certain kind of combinations of, I'll just say, a window, a door, and your garage door, when they're open or closed, what would be that everything is secure, and in other cases it would not. And so in this case, there's 3 specific examples of when it's okay, and the rest of them are 0. So assuming that 1 is true and 0 is false, to give you that example. Well, how could we actually implement this in digital logic? Anybody have an idea of how you think we would go about doing that? I'll show 3 examples in the next couple of slides. And so this is from Stalling. And hopefully as a result of us going through the material in this chapter, it'll become a little bit easier for you to figure that out. But this is one of the things you can do. You can actually have this truth table, and you can have a piece of software that would generate the electronics to make it actually happen. So here's an example of how we could be doing it with AND gates. And so we actually haven't introduced this yet, but you can, it's sort of a shorthand for an AND gate with 3 inputs. You could actually, what it is underneath, it's 2 AND gates. And so, and then we have these inverters, and depending on which wire that we put this little bold dot, remember that means when there's a bold dot, there's a connection. If there isn't, that means that there is no connection. And so thus we can see a certain arrangement of those combinations is reflecting what's shown in this truth table. And so we're going to be seeing this a lot in the next handful of charts. And so this is using AND gates. And so here's another example where we're using OR gates in an AND gate. This would be another possible way that we could do it. One of the little shorthands here is we see that little line on top. Anybody remember what that means when you show something that has a line on top?
Like the inverse.
Yeah, it means it's an invert. So this would be not This would be not C, this would be C, this would be not A. And so those are two examples. And then we have this other one. This is the minimal number of gates that it would take, assuming that you just have the not A and not C. Otherwise, you would have an inverter on both of those. It would be another way that you could implement that. Okay, I'm not going to get into details about Karnaugh maps, but I think what you'll see in the next few slides, it can give you an idea of what these different relationships can look like. And so this is an example here. So the first one is not A, B, and D. And then you could be drawing a circle around those to give you an idea of what it would look like. And we're showing this as a square, but almost maybe you should be thinking of it in terms of like a ball, because this means that this one up here and this one down there are connected. And so it's like it wraps around for you to be seeing that. You can have overlapping groups. And so this would be a way of how you can be visualizing these Boolean algebra expressions. So that's just a little bit of some perspective on that. This is a truth table for a 1-digit packed decimal incrementer. And so this, it's what it's called, another way of calling it is binary coded decimal. Anybody ever heard of binary coded decimal? So if we have 4 digits, we can have a unique way of showing 0 through 9 in those, but there's other ones. What is it? Anybody remember what a hexadecimal is? Isaiah, remember what hexadecimal means? Yeah, it's 16 possibilities. And so that's the reason why there's 16 here. But if we have binary coded decimal, we're not using A, B, C, D, and E, and F. And so that's why it says that you don't care the condition. And this way, we're figuring out a way of encoding in binary using 4 bits, these 10 states, although you could code up to 16. That's just a little bit of a reminder there. So these are the kind of things that you can be doing. Another method that I'll just skip over here is also installing that you can look over. So there's multiple ways of how you can be going from a table like this to coming up with an end result that's something like this. These are going to look, I'll focus on this one. This one looks more like, well, based on what that input is, it's going to be a matter of which one of these I'm going to put this dark circle in to make those connections. And when we talk about a FPGA in a few minutes, that would be the kind of thing that we're looking at. So skip over this method. Now we have yet another example of the implementation of this table from 12.4, one that we have here. So we have had 4 examples that we're showing that gives us a sense of what's going on. Here we're just using 3 NAND gates to come up with that result. Okay, now here is a multiplexer. And so let's explain this, and let me see if I can have one or more of you guys help me out with this. And so anybody familiar with a switch? You turn a switch on at home. Anybody see a 4x1 switch? Is that something you've ever heard of? What do you think a 4x1 switch is?
Not like a series like a light switches, or is it 4 different lights?
Yeah, Paul, that's getting at what we're getting at. And so what this would mean is I have like 4 inputs and 1 output, and depending on if I have it switched up here, then D0 is going to come out here. If I have it switched here, then D1 is going to be connected to F. if it's connected to D2, it's going to be connected there. And D3, that's connected there. So it's like basically, so how many possibilities would we be able to have if we have two inputs where each one is 1 or 0? Anybody remember what that would be? Yeah, to the 2. So, so this, it would be 0, 0, 0, 1, 1, 0, and 1, 1. So that means there were, depending on these signals, it's going to tell us which one's going to route from the input to the output. Does that make sense? So this is an important capability that you have in computers, is you need to be selecting things. Remember, we talked about an arithmetic logic unit. And so this just gives you a little bit of an insight of one of the things that can be done for that. Here's showing you that 4 to 1 multiplexer truth table. And so 0, 0 would code for this one. 0, 1 would code for D1. 1, 0 would code for D2. And then finally, 1 and 1 would code for D3. That makes sense?
So I get like the inputs, like if you turn on one switch, it goes, that gets outputted. What does like the S mean again? Those are like the signals.
Yeah, these are the control lines.
So what does that help do?
So that's what this is. This is the one that effectively makes the input go to F. So whatever state is D0 is now going to be what F is. And so if this is 1, then F will be 1. If this is 0, then this would be 0. If we select it for D1, if D is 1, this is 1. Doesn't matter what D0 is or these other 3 inputs. All of those are ignored. That just gives you an idea what a DMUX is doing. Okay. Now this is giving you an idea of a multiplexer input to a program counter. So multiplexers are used in digital circuits to control signals and data routing. So an example is loading of the program counter. The value to be loaded into the program counter may come from one of several different sources. So you can have a binary counter, that would be possible, the instruction register, the output of the ALU, the arithmetic logic unit. And so that's what we're trying to show here are what are we trying to have loaded into the program counter? Where is it going to come from? So we're showing that there's 3 inputs. And so based on what those control signals are doing, it's going to determine what's going to go in that program counter. Does that make sense? So we're showing how a MUX actually is used in routing information for part of our architecture. So we can have not only 4 inputs. If we had 2 to the 3, we can have 8. And so we can have, now we'd have to have 3 inputs, and that's going to have it go to one of these 8 outputs. So we can be taking that to the next level as we move forward. This is the same kind of thing that then starts to help us to figure out, well, what is the address we want to decode? So remember when we talked about memory? How do you look up a specific memory address in our RAM that we have in our computer? Anybody want to take a guess on how that would work? Connor, how about you? You want to give your thoughts on how you think you would implement that?
Sorry.
How would we determine what location we want to get information out of RAM? How would we come up with an approach to make that happen in a computer? Does anything that we've talked about here sound like it would be useful? How about I go back to this figure here because I was focusing mostly on that. So this is what we're trying to formulate the address here. And this is the different locations in memory that we're trying to retrieve. How do you think we would go about and retrieve that information?
Using the portal one.
Yeah. So basically, I could select one of these 4 memory locations with this address. And it's going to report out at the output. And so this would be just one bit of information. So how do you think I would do this if I wanted to have 8 locations, 8 different memory locations? What would that require?
8.
Yeah, so there'd be 8 here. How many lines for address lines would we would need? 2 to the 3 is what we would require. If we had 4, it'd be 2 to the 4. How many would we be able to have then? Yeah. Mm-hmm. Is that starting to make sense? Does that make sense, Connor? Okay, so that's what's starting to get here. Now we have these address lines, and so we're going from A0 to A9. Now we have 2 to the 10. And so what we're doing here is we're selecting what address within 2 to the 9 bits of information that we have available to, that's the one that we wanted to get. Does that make sense? So it's just an extension of what we had with this simple diagram here that we show.
So
Yes,
the A's, the inputs, or is that the RAMs?
this is the address lines. So they're calling them A0 through A9. In this earlier chart, we were calling them S1 and S2.
Those are like the signals, I guess.
Yeah. So if you caught that, then I think you're starting to see how we could do that. So you can have going from N to 1, or you can go from 1 to N. And so now this is like you're putting this kind of device here in reverse. So basically there's only one output. If we did a demux, what we would have there is that, say, now the information flows from inputs to outputs, and so it flows like that. So if I was to draw a demux, it would look like this. So there's one input, and there'd be 4 outputs. And we're going to have those same inputs. And so what you're going to be doing is you're routing a single input and go to one of 4 locations. Okay, so this is a mux and this is a demux. And so that's what we're talking about next as we think about more of this material. So now if we have, what is the difference between read-only memory and random access memory? Anybody remember that? Why would we want to have read-only memory? Anybody have a thought on that? Go ahead.
Like when you don't want someone writing to that number.
Yeah. So the thing that I like to consider, and it's for the most part, it's true, is like you have like your BIOS in a computer. Anybody know what the BIOS is? Is that some of you have made a computer, you've probably seen that. If you don't have an operating system, what does your computer do if you turn on? Anybody ever had that happen? Maybe your hard drive wasn't put in, or something happens when you have your motherboard. Anybody have an experience with what happens with that? So it's going to have some basic function that's going to be able to show something on your screen. It's usually what it has. It has a configuration item of things that it needs it'll do a self-check. And so what it's doing in that self-check is it goes through this kind of things. And so it's going to do first, just check that, okay, is the memory okay? Is there a hard drive there? And it'll go through these things and it'll report back whether or not everything is functional. This is also a place where you can have some basic functions, like what is it going to boot up to first? And so those are some of those things that would be utilizing in that. So that would be something that you would want it to not change. One thing with modern BIOS is you have the ability under special circumstances to write over some of that information. But other than that, this is what we're referring to. So here can be an example of a truth table for a ROM. And so I tried to make it a little bit easier to see. So the yellow with the red numbers are where it's 1. And so there's a lookup between the input and the outputs. And so this is, in one way, is maybe easy to conceive, but here's another way of looking at it. And so there is a relationship between when you look at a certain part of this, that this shows how the memory could be implemented using a 4 to 16 decoder and a 4 OR gates. And so that would be one way to be thinking about it. So a decoder is just another related word for a demux. And so you can use whatever word that you find is better for you to get a sense of what's going on there. So you can implement this type of a truth table, and thus we can see this is what it will look like, one way of implementing that in hardware. So the thing is, this is general, this crossbar kind of connection, and it's where we have these things these are where we program it, is where we make those connections between the input and outputs. So when you call up a certain address, that there's going to be a certain value that's going to come out. Okay, so then here is something interesting that we can do in addition, using this kind of a construct here, with a read-only memory. So when you put in a certain set of inputs, you're going to get the outputs. And so this is what we can see. So based with these 2 inputs, this is what it's going to produce. And so thus we can have either a single bit adder or doing an adder with a carry, both for the input and the output. Anybody remember what that carry in and carry out means? So what's 1 plus 1 in binary? Anybody remember that? You're actually both right. So the carryover would be 1, and then you can only have 0, 1. 1 plus 1 it would be 0 for that 1 bit, but you're going to have something that's carrying over. That's what it is. And so if you have multiple bits you're trying to glue together, you're going to have an input. Is there something from the previous lower level number? And are you going to be folding that into something after that? And so thus you could start to be hooking things together. A 4-bit adder is aggregating 4 1-bit adders. Does this make sense? You seen that? And here is an example using digital logic of one way of conveying what that kind of what that would look like. And so you have the sum, and you can have the carry. And so this is going to be some of the stuff that we would be carrying along with this. And we can make them larger and larger. And so this just gives you an idea. This is a 32 bits. And so it's, so we're hooking together 4 8-bit adders. So we had a single bit adder. Then we put that together and we have a 4-bit adder. If we made that a little bit larger, an 8-bit, we can hook those together. So now we can have a 32-bit adder. So this would be one of the things that you would have in an arithmetic logic unit. Anybody remember what an arithmetic logic unit is? what's an example of a function you can do with an arithmetic logic unit? Anybody have an idea? Add, you can do addition, right? You can do multiplication. You can do Boolean operations and or. All of the things that we're starting to see with our Mars MIPS emulator, we're seeing that those are the kind of things that can be done. Okay, the next thing that we're going to talk about, and I'm just going to go through this fairly quickly, is a flip-flop. And so what do you guys think a flip-flop does? Anybody want to venture a guess what that is? I'll show you a picture of one. The fact that you're routing the output back to the input, this is a thing because what happens is there's a time delay between something that's coming into the input and when it goes to the output. And then when you route it here, what actually happens, it starts to remember a state and it maintains that state. So we use flip-flops to help us to remember bits of information. So this is using digital logics, how we show, how do you maintain a memory of that state that you've encoded it to, either to a 0 or a 1. So we have a latch, which when we, can give you an idea of how it would work when you're loading information into that latch. So you have that. Here's some other examples of if you have a latch and you put this other electronics too, this gives you a full-fledged flip-flop, and it's going to remember the output. Whatever was the condition when a clock comes in and the data that's supposed to be loaded into that flip-flop. So there's a couple different types. I'm not going to get into this for right now. I'm just trying to think generically of what we're trying to do is remembering a bit of information and showing how that would look in digital electronics. Here, here gives us the basic flip-flops of relationships between the inputs and the outputs. And so we then start to put those flip-flops together. And so this is where we start to get the register. Okay. And so here is an 8-bit parallel register. Remember what does a CPU have? Does it have registers? Yes or no? You guys remember that? Okay. Then we have a counter. And so what, anybody use a counter in their digital logic project? I think you did, Nathan. Remember, what does a counter do? Counter counts, right? So basically it goes 1, 2, 3, 4, 5, 6, 7, 8, however many digit it is, and then it may just recycle, go back to 0. And so that can be a useful thing for a computer. You can think of a clock as another example of a function that you need to have. And so we have a little bit of an introduction to that in the textbook here to give us a sense of how we can go about doing counter, designing a synchronous counter. So going 1, 2, 3, 4, 5, counting up. And you can read installing for a little bit more information about that. Okay, this is now just looking at a more generalized sense of what we showed earlier, so we can have a general layout for a 3-input programmable logic array. And then we can start to make these connections. And so this is now a programmable logic array for these equations that we're showing here. So we can have A, B, not C plus not A, B. And then we have not A, B plus A, not C. And those would be an example of something that we would like. So we could go back to this table that we had a while back in the lecture for today. here is a basic truth table. And with this PLA, this is the kind of thing that we can actually program. And here would be the output of saying this is what we're looking for. And then a more generic version is something called an FPGA. Anybody ever heard of an FPGA? Okay, some of you guys have heard about it. In the future, this should be something you'll encounter. And so this is another way of, with this same kind of approach, you can actually program complex kind of operations that cause an effect that you select a certain amount of inputs in a certain way, it's going to give you the result. And so this is actually something that's used for a lot of complicated type of computational things that you can lay out, and then it's codified and used again and again and again. So that's what I wanted to just to give you an idea for the contents of this chapter, to be thinking about digital logic. And I was trying to keep it at a high enough level that hopefully folks weren't missing the big picture of what we're trying to convey here. So it's all based on Boolean logic. Now we can see there's a relationship between what we've done with our digital logic designs and our projects. We're conceiving them in gates, and then we have these other types of things that when we start to aggregate together, this is going to be the stuff that's going to help us to make a successful computer architecture. Any questions on that? All right, well, let's see if we can do something that might solicit a little bit more participation in the course interactively in our session today, because like I mentioned, we're trying to have Tuesdays be more of an engaging time where we're thinking together as a community. And let me go ahead and pull up our project slide here. Thanks in terms of the great project work that you're doing. So, well, let's take some of these are I think one or more of these the feedback I've been getting, you guys are going to be updating them, but I'll just take this verbatim for now. One of you guys were thinking about doing various types of calculations, so I'm just going to call it a calculator. So what do you think would be the things that you would need to do a simple addition calculator? What are some of the things that we've covered today that would find that necessary for us to accomplish that? Yeah. So you're going to have to mimic the capability of an ALU, maybe not all of that function. If it was just going to do addition, for example, then you're not actually, so let's just start something basic. And so you're going to have the ability with your controls to say that we want to add what? You want to be thinking of two inputs. So how are we going to store those inputs? How do you think we would be storing that information? Yeah. Yeah, so we would be using registers. So we talked about a register. And so we're going to have to be making a register. And we showed an example of how you could be doing that with sequential logic. Okay. So that's the first thing, is you need to have inputs. And let's take what Paul was saying. And so let's say it does more than just doing addition. Then we need to know, well, how many functions does it actually do? So it does addition and subtraction. How many bits would it take to do a decision between addition and subtraction?
How many bits?
Yeah. This isn't a trick question. There's just two items. So how many bits would it take to It would take 1 bit, okay? Let's say if we wanted to do addition, subtraction, multiplication, and division, how many bits do you think it would take to do that? It would take, you need to have 4 unique values. And how many bits do you think it would take? Yeah, it would take 2. 2 to the 2 is 4. Paul was saying there's 4 values. But if we wanted to be actually efficient in terms of how we're having those control lines, we could do it in just 2 control lines. That's my point. Okay, then we need to have an adder. And we talked about an adder in what we covered today. So we'd have registers, we'd have control lines for it to have the function. And if we wanted to do an addition, then we'd go to some kind of device. Well, they talked about a couple ways you could do it. You can actually just have something like this, where you have a lookup table. In an earlier, something else that we showed, you can actually do it with discrete logic. And gates and OR gates and inverters, but this just gives you an idea of how we could start to conceive of doing a calculator. How are the numbers going to come in? Are they going to be in binary? Are they going to be in decimal? And so if they're in decimal, we're going to have to convert it to binary, because that's the way our computer thinks. You're starting to see there's a lot of things that have to be hooked together for us to do a functionality on that level. Does that make sense? Anybody want to offer up what you're doing in your project, one of these 17 items, and we can talk in that context and see if we can figure out what we've gone over today, how that would apply? Paul?
For me, I'm number 8, so
Okay.
in the case of like cards, the main thing I was saying like was like comparing them in different ways.
Mhm.
So it's like the way that Yu-Gi-Oh works, that like they release different cards
Yeah.
that do different things, right?
Mhm.
And one of the cards that came out like kind of recently, like specifically cares about each card having one specific thing in common out of like,
Yeah.
5 different traits, right?
Mhm.
So I was looking at earlier the like logic tables,
Right.
and I was thinking like, because I was trying to think, how do I like use digital logic to determine if like 2 different cards have exactly one trait in common and nothing else? And I was like getting it kind of working with like the wires and stuff, but it was like such like a mess of wires, like I couldn't really like understand like what I was making, so it was just like everything was overlapping. So I
Mhm.
was like, okay, I'll just try using this table instead. So I
Yeah.
did that, and then that like was a lot cleaner.
Yeah. So like what you're saying, and hopefully everybody's following what Paul is saying. And so he's trying to compare cards, UGO,
Yeah.
UGO. Okay, sorry for some of these games I don't know,
Yeah.
but so if you like, one level would be comparing, are they the same card? Okay, that sounds like an AND gate, right?
Yeah.
It's, you can do a logical, are they the same? That would be one level, and that layer below that, and then it has 5 traits. So which of those 5 traits does it have? You know, that sounds like 5 different bits of information that we're trying to look at. And so it could have 1, it could have 2, it could have 3, 4, or 5 traits that they have in common. So you could see that would be another layer of how you could be figuring out how to be doing some of that coding. I always like to talk about going from success to success. So maybe having that one simple case of one aggregation. So are they the same card? And getting that to work. But if you have 5, you're going to see it's going to be more complicated, that you're going to have to be looking at, 5 of these inputs, and then have some kind of a truth table that you would be doing with that. So I'm glad that you're starting to see how this could come together. Have you thought about, I presume this may be, or some subset of that may be what you'll be doing in your Arduino unit. Maybe you might think about doing that in your Mars MIPS as well. But you remember that the Mars MIPS, you're trying to think of from a CPU perspective. Does that make sense? How do you think you would start to conceive that, say, in your Mars MIPS program? Any ideas?
I'm still like totally sure. We talked about this a bit last week, I think. Where like we were able to just sort of like compare specific numbers and see if like they're the same or if they're different. And that's
Yeah.
sort of basically what we do it.
Mhm.
So
So you could compare it number to number, or you could do an and or an or operation, just comparing those two registers. And so there would be two options, like, that either one of those might be easier for you to implement, and you could be thinking about that. Does that make sense? Any other observations that you have, Paul, you wanted to make about your project, and maybe just think about this information from that point of view?
I guess like, so for the Arduino, I'm not like totally like concrete on what I
Mhm.
want to do just yet. I was thinking about, last semester, I used an Arduino kit and I
Mhm.
used like the internet function to connect like an API. and
Yeah.
I was like connected to info from the API to like display on the LED,
Mhm.
but this time around, I feel like if I'm comparing cards, I can use, because there is an API that has every single.
Yeah.
card. Something like, if I can like connect to that and I would just have like an easy way to like look up this card and see if it like
Mhm.
with this other one, right? I think that'd be an interesting functionality.
Yeah, and so just like think of a CPU doesn't do the whole, it doesn't do everything. And in one way, in isolation, it seems kind of dumb. It has to have things submitted to it in a certain type of format, and it's only going to send that information to another register. Then you have to pick that up with other parts of your computer architecture to make it work. So it's an abstraction that you want to be thinking about how you're going to apply it to your project. So in your Mars MIPS project or your Arduino, how are you going to model having a card? Maybe it's just going to be a toggle button. Maybe it's just going to be one bit of information. It's either 1 or 0. And then you have to be providing that interpretation of what those things mean in the context of what you're trying to do with your project. Does that make sense? So, anyone else want to mention their project? And we could talk about that in the context of what we're covering today.
Just talking about like the overall project with them, or like.
Yeah.
Mine's like number 13 for the
Mhm.
sensor matic system. And pretty much like the digital logic display I did. I just made like 2 or 4 different inputs based on the design of
Mhm.
it. I did like 2 different doors or 4 different doors, and I guess what they do is like in a way to detect motion. So like if someone walks
Yeah.
through the door would open basically, and then as soon as the person walks out, door just closes. So I kind of just want to make a function of like detecting on the system if the door is open or not. And so I kind of started that a little bit for project 2. Kind of made that little function where or I guess like inputs or registers, I guess like to check if like door 1's open or door 2's open, and
Mhm.
then compare that based on like 1s and 0s. And so basically I wanted like 1 to be like doors closed and 0 to be door open. So like I would compare that, and then like if if one door says like it's 1 or one other door is 0, then they'll pop out a message like, hey, this door is open.
Mhm.
Do you want this to be closed? And then they'll keep looping that over and over until I do it.
Yeah, well, let's think about Nathan's projects. Basically a home detection system and having the sensors that would support that. And so in the digital logic, basically it's like an analog computer. It's taking these inputs and then coming up with an answer. Well, it's actually it's implemented in digital, but it's just using that hardware. It's basically a hardware only type of capability that we're looking at in terms of getting a sense of how we're going to do it. And the result is, one way to think about it, he would have a truth table like this to come up with, this is under all these possible conditions, what is going to be the output, and a certain combination. And I think the way you have it, it would be that when all 3 inputs are true, then it would be true on the output. Okay. Well, now let's think about how we would do that from a CPU centric point of view. Okay, the CPU can't get anything to the registers. That has to be provided to it. It's once you put that information in the register, that would be the input. So there's no toggle switch or something like that. You have to do a command to load a register with information. Then after that, you can do a command that's going to activate the ALU to do a compare function. So an AND of A, B, and C, and then it's going to figure out what that result is. That's going to be the command to do something with the ALU. And then you can have to load that to another register. And that's all that the CPU does. But for us, we then want to take that information and make it readily available for us to interpret. So if we put it on our screen, if we light LEDs or something like that, that gets into the Arduino part of what we're trying to accomplish. Does that make sense? So we're going to be seeing it from different vantage points as we go through these different types of projects as we're progressing through the class. Anybody else? How about we get one or two other folks that talking about their projects? Who's doing the wearable fitness tractor? I don't remember. Okay, go ahead. Why don't we just think out loud to think about where we're going with this, and let's see if I can make it more real for you and everybody else rather than having these abstract concepts we're talking about in class. So tell me a little bit about your project and let me see if I can help out some.
Yeah, so the wearable fitness tracker, so like I'd like to have a timer on there. So
Mhm.
clock,
Okay, pause. Timer sounds like a counter, right? Okay, so now we're relating that. Go ahead.
the heart rate. As well.
Hmm.
That would also have to do with like a timer too.
Yeah. So heart rate monitor, so you're getting an input. And so you're sampling like every 60 seconds. And so how many beats did they get? And so every 60 seconds, you have to check a register, for example. The CPU is commanded to count. Okay, now go after so many clock cycles, go in and get the information in that register compared to the last one. So just you're thinking in terms of how is it actually done in a computer architecture? So
Yeah. I was also like calories.
Mhm.
So somehow I don't know how I would do that yet, but I would definitely like to keep track of like a calories while being.
Yeah, well, let's break that down a little bit. So this is one of the things I like about object-oriented programming. You can think in terms of abstraction. So you can abstract it at the highest level that you can still get the basis of what you want to do. You can fill it in later as you go. So the highest level, we're not going to be having a fancy device that's going to cost hundreds of dollars to figure out, physically going in and figuring out what is your basal metabolic rate, and to figure out how much that is, to sample all of your food and figure out how many calories that is total. We're just gonna, the highest level would be to say let's just stipulate that that's a number that we're given. Okay, for a CPU, once again, that's all it does. It just reads and writes to registers, and based on the stuff that it's being commanded to do in its arithmetic logic unit. So let's just say heart rate, something's fed into a register, you then have a counter and you sample that periodically. Caloric intake, at the highest level is that's just a number that you feed in. So now you have heartbeat. And so maybe what you're stipulating is you want to get your heart rate up to, 150 beats per minute when you're working out and sustaining that for 30 minutes. And you want to have a caloric intake, your basal caloric intake is 2,000. And so if you're in training, maybe you want to boost that to 2,500 or 3,000. And you're starting to figure out some of these values you put together and make this start to happen. So continue on. Let's just kind of think about how we might actually do this.
Another one was, I think this one pretty like just a step counter, so.
Yeah. Mhm. Yeah, so that would be an example of something that's coming, like say, like you're using an exercise, piece of exercise equipment. So there's one of the, it shows you that on the display for the workout equipment. There has to be some way of feeding that information into your device, what you're doing. So once again, the highest level, start with something simple, make it work. That's just a number that you type in on your console, and then you can start to do more sophisticated implementations. Like what I always talk about each of these projects is you have three sub-elements, a real basic one, and then you can extend it a little bit further and extend it a little bit further. So go from success to success to success. Yeah, so like the first one might be heart rate, second one might be caloric intake, and third might be taking in the information that you're getting from this piece of equipment. And it's first of all started very high level abstraction. And that's part of where the genius of creativity is, of thinking of how you're going to do that. Some of you guys are taking software engineering. And so this is where you start to be thinking not only just the programming, but thinking about the larger context of what this is about. And this is a piece. Does that help?
No, yeah,
So.
yeah, we're pretty much all the main components out.
Yeah. So for the digital logic, it could be just three inputs. The above a threshold, that the heart rate is high enough. And so you have a one for that. The caloric intake, that they got enough because they want to have an elevated caloric intake for training. And then you have one for the exercise equipment, that they have reached their goal, that they worked out in the treadmill for 30 minutes at a rate of 10 miles per hour, something like that. And so you have those strings together, and that's your inputs for that. Then we think of it from a CPU point of view. Once again, on its own, a CPU can sound kind of dumb. It just reads and writes to registers. It does things in the ALU that it's been programmed to do, and then it spits out that result, and it's ready to get the next step of instruction that the program is going to dictate for it to do. And so sequential element in the program, one at a time. All of that is going to happen. You guys tracking? It's just giving you a sense of trying to be thinking about these parts of your computer architecture. And Stalin also does a great job, and sometimes it's overwhelming. He goes like 2 or 3 levels into the details of how it works, and you're being exposed to this in the survey portion of this course that I hope you're starting to pick up. Okay. Well, let me go back to the overall summary slide for our chapters, and just make a few more comments here to help you get a sense of what we're coming up to next. And so there's various ways that you can be putting it together, but this is the way we have in our class here. So now we've been starting to think about how we're going to convert things, digital logic, how we're going to make decisions, how we're going to store information. Now we're going to be getting into thinking about the instruction sets. And so starting on Thursday and the next several lectures, we'll get into the instruction set. So remember, we have an x86 based instruction set. We have an ARM based instruction set. We're using the Mars MIP, falls into the ARM family. And so this would be information that's used to tell what the ALU is going to do. This is like telling what register we're supposed to be getting information from or sending information to. Those are just a couple examples of what's going to be in these instructions that we're going to be utilizing. How you do a decision. Is it equal or not? So that's an example of the kind of things you can do in assembly language, equal or not. So you have to pose a question to the decision part of the ALU that it's either going to have a true or not, equal or not equal, rather than the more flexible ways in a higher level language of how to do various decision making and branching. And so that will be the next thing that we get a chance to be thinking about here. Any other thoughts? Okay, I think that's a good breaking point. If you haven't already, please get your Arduino kit as soon as possible. For some of you, especially the computer science folks, it may be a little bit overwhelming. we're gonna try and simplify that, but also let you get a chance to touch the hardware. And so you can get a chance to see what that is. The engineers, this is probably like your home base, you love it. But you also want to be doing this cyber physical thing, put it all together, and that's where the magic is gonna be for us, okay? All right, thanks a lot, you guys.